some important definitions for probability. An event, an outcome from a random experiment, and probability is measuring how likely an event will happen. Does it make sense that probabilities will never be bigger than 1? Right? I'm 110% sure. Sometimes people say things like that to like overemphasize, but that actually doesn't make sense. The greatest probability is 100%, which as a decimal would be 1, and impossible would be 0. What are the chances it would snow today? It's kind of nice. It's pretty nice. Yeah. Sample space is a set of all possible outcomes of an experiment, while an event is a subset of the sample space. Okay? So we could take this class, and all of you would be the sample space. But if we said, how many people, we get into debates already, how many people like Hawaiian pizza? It's like, should pineapple be on a pizza or not, right? You get into that very divisive, right, fights. Maybe I should not bring this up. I don't want to have any injuries. I'm generally not a pineapple on pizza fan, okay? But I'm also generally a person that's not very fussy. So if it's a choice between not eating and eating Hawaiian pizza, I will eat the pineapples off of there. So, but a sample space would be like an event A, people that like Hawaiian pizza, that'll be part of the whole sample space, that event. And we have these diagrams that show what's happening. So example here, we got Hawaiian pizza here. Maybe we have 9 people out of a total of 18 like it. So we put 9 in that circle and 9 outside of the circle to say there's 18 people in total, 9 like Hawaiian, the other 9 don't. And we'll start using these diagrams and putting numbers into them to help us understand what's going. Listing sample space, listing all the possible outcomes. Okay? Now, we're not going to get crazy here. Okay, every year, toss in a coin. We're going to just say heads and tails. But eventually, it could land on its side. You could throw it up in the air. A bird could take it. Yeah, okay. But generally speaking, we're going to say toss in a coin, heads and tails. Okay? If you come into class and you can toss a coin and land it right on its edge for me, and you write that on a test, and you say, it could happen, well, then come in and I'll give you 10 tosses. If it doesn't land on its side once for you, then you're out. Okay? Right? You could, rolling a 6-sided die. What is our sample space? 1 to 6. We're not going to imagine, let's see here, could we even balance it? All right? Now you're going to go home and you're going to try and balance it on its edge all day. There's probably someone on YouTube who's done it. Good for them. 0. That's why our sample space is 1 through 6. Ooh. Now you're like, I'm having so much fun in class, flipping coins and rolling dice. I want to do those things. This time I'm doing 2 6-sided dice. How many possibilities are there going to be? 36. I could have got a 1 and a 3. I could have got a 6 and 3. How do we write that sample space and write out all the possible sums, well, we could do a chart. We got our, here, this is our red dice, because I had a red one, and this is our white dice. Imagine I circled that in white. And the possible sums. And so, you've got a lot of games deal with probability. One game in particular that I can think of that uses these numbers. How many people have played Settlers of Catan? Couple? Yes? Okay. If you notice on the little, in Settlers of Catan, you roll a dice to find out whether or not you get a certain resource. And on the resources are numbers. So for example, they have the number 6. And in Settlers of Catan, you learn that 6 is a good one to be close to because it's more likely to roll a 6 than it is to roll a 2. The next time, if you have played it before, the next time that you play, you will notice that under the 6, there's 5 dots. That represents the fact that out of 36 times, a 6 happens 5 times. And under the 2, there's just a single dot. Oh, thank you, thank you. Under the 2, there's just a single dot because a 2 only happens once. If you haven't played Settlers of Catan, you should find someone who has played it. It's a very, very good game. So then you look at this and you say, well, what is the most likely thing to roll? Can you see that a 7 happens more often than any other number? The theoretical probability of an event occurring is based on the following calculation. The number of outcomes in which event A occurs, and the total number of outcomes. So what are your chances of rolling a 7 when you roll 2 dice? Well, the 7 happens 6 times out of the 36. There's a 1 in 6 chance of a 7 being rolled. Does that mean when I roll the dice 6 times, I'm guaranteed to get a 7? No. That's experimental probability, when you actually do an experiment. The idea with theoretical and experimental probability is if you do something long enough, it eventually will get closer and closer to the theoretical probability. So there are some things that we can easily do the theoretical probability. Dice, for one, because we say each of these sides is equally weighted. You've probably played a board game once where you felt like something's wrong with these dice. Just doesn't seem to be working out right for me. But the idea is each of them are, you have a theoretical probability for each. So here's our probability of a 7. And then if the probability of event is P, if you do a number of trials, you would expect the event to occur n times p times. So here's our probability of rolling a 7, 1 out of 6. If you did it 100 times, you would expect to get a 7 16.67 times. Well, that can't actually happen, right? But you would expect it to happen around 17 times. That doesn't mean if you do it 100 times, you will get exactly 17 times. In fact, that's one of the things that we're going to look at in this unit. If you rolled the dice 100 times, we'll be able to figure out what's the probability that you rolled a 7 exactly 10 times. What are the chances of that? We'll be able to figure that out. So it's some pretty cool math and probability that we'll get to. But not yet. You have a 20-sided dice. Sorry, I can't show you an example. The best I have here is a 30-sided dice. Okay. Oh, bonus mark. Does anybody know what a 30-sided object is called? Bonus mark on your next test? Oh. It's a rhombic tricontahedron. It's just on the tip of your tongue. The most useful word you'll learn all week. Okay. Oh, you don't remember? You have to rewatch the video. Okay. Event A is defined as the number obtained is a multiple of 4. Find the probability of A. Well, you could get a 4, 8, 12, 16, or 20. So your probability is 5 out of 20, 1 out of 4. If you roll the dice 100 times, how many times would you expect to get a multiple of 4? 25 times. We'll be able to use probability to say why, it's not good to just guess on all multiple choice questions on a test. Your chances of passing are not very good. But we'll be able to figure out exactly what your chances of passing will be. Experimental probability. It's the measure of likelihood based on experiments. So same idea, right? How many times does something happen? Divide by your number of trials. Right? So, here it is. I'm going to roll 6-sided dice. I'm going to do an experiment where I only do one trial. I'm having trouble rolling a dice today. Oh, I got a 2. I now know that on this dice, your chances of rolling a 2 are 100%. Guaranteed to get a 2 every time because I did an experiment. I rolled it once, I got a 2. Therefore, I have proven that you will always roll a 2. There, just double check. Yes, did it again. Worked out perfectly. So your experimental probability, the number of times an event was observed, and the number of times a trial was carried out. The ratio above can be called a relative frequency of an event A. You can use it as an estimate for the theoretical probability. But as you saw with my experimental probability of one roll, having not very many trials does not give you a very good probability. Okay. You toss a fair coin, heads and tails, 10 times, and you receive heads 7 times. Experimental probability is 7 out of 10. Theoretical probability should have been 1 out of 2. Oh, I got 7 out of 10. Okay? But then, I'm sorry, I'm always thinking about ways of stealing money from students, but so if I flip the coin 10 times, okay? I'll give you, would this be a good bet to do? If it happens 5 times out of 10, I give you $5. If it doesn't, you give me $5. Would you take that bet? How about if I give you $6 and you give me $4 for 5 out of 10? When would you take the bet? At what point does it make sense for flipping this? I got head once. Oh, no, I'm not going to do it 10 times. It's going to take too long. But I could do it 10 times, and we could find out. Oh, we could set it up on our thing really easily. Here we go. Escape. Set up our, yes. We could toss coins. Heads or tails. Set. Trial set, score table, update after, and okay. So once plus 10 more. We just have to subtract 1 off of the, take away 1 from the tails because this one doesn't count. Oops, I have to hit this button. 10 more. Oh, it happened 5 times. I'd have to pay you money. Shoot. Okay, sorry. Example number 2. So you are sitting in the front corner of the school, supposed to be doing your math lab for Friday, but you're bored, so you start counting cars that drive past the school. And there happens to be 45 red cars come by, 16 black cars, 2 yellow cars, 14 green, 17 blue, 23 gray, 21 colors that you did not know, so you just put them under other, for a total of 138 cars. What are the chances the next car that passes by the school is red? Well, according to experimental probability, you would say there's 45 out of the 138 that have been red, so my chances are that the next car that's red is that number, or 15 out of 46. That's using your experiment to tell you what you think is going to happen next. So the next morning, you still haven't completed your math lab. You're still sitting at the window counting cars. Okay? Estimate the number of red cars that morning. So then you would take your experimental probability times the 356, and you say, seems likely that there would have been 114 red cars that go by. So often, we will use experimental probability to help us predict things. Does that mean that that's exactly what's going to happen? No. But it might give us a good indication. The bigger your experiment, the more likely something is to be true. So we'll see right now that they're using lots of statistics because there's an election coming up. They're trying to predict what's going to happen. So they phone people and say, how are you going to vote? They don't phone everybody because that would take too long, right? They find out from everybody when the election happens, but not everybody votes. So they use those predictions to try and say, oh, this person's leading. So then they have to go, oh, we're losing in this part of the country. We need to go there and do some more experiments, or do not experiments. You don't. An election, you're not like, oh, we'll do an experiment on these people in this town. What if we put this in the water? Do they vote for us? No. But they do different kind of techniques to try to win things in certain areas. They change their policy to see, oh, by changing this, we get votes here, but we lose votes here, so maybe that helps us. So a lot of statistics are involved and probability at those points. All right, this is where